Alright, ladies and gentlemen, this is our bonding review video in which I'm going to go over the topics in this bonding unit. So please excuse the voice, I'm still recovering from a sore throat, but here are the topics in this unit. We're going to go through each of them. And then we start with this slide about stability and energy. So the purpose of bonding is for elements to achieve stability. And so for an atom to reach that level of stability, it must have 8 valence electrons. Except hydrogen and helium, they need only 2. So in order to reach that 8 valence electrons to be like the noble gases, all these other elements have to either share or transfer electrons with each other to form bonds and therefore achieve stability. And when you form bonds, energy is being released. So remember in class, you imitate the clap, you bring two things together with a clap, and then your hands and fingers flutter around and you see a release of energy. Okay? But when you release energy, you have less energy now. But being with less energy means you also are more stable, higher stability. So bonding is the purpose for stability. Okay? The purpose of bonding is to reach stability. On the other hand, when you're breaking bonds, imagine you're getting angry. So like Goku going Super Saiyan gets angry, and you're absorbing energy to reach at a higher level. And then when you absorb that energy, you have the energy to break the bonds. And when you break those bonds, you have more energy, but you're also less stable. So going the opposite direction of stability when you break those bonds. And so we have multiple types of bonding we explore in this unit, and the first one we talk about is ionic bonding. So ionic bonds involve the transfer of electrons between metals and nonmetals. And so metals are the ones who give up their valence electrons to the nonmetals. The metals are the cations. They lose their electrons. Oops, let me bring it out here. So they're the cations, they're positive. And then the nonmetals are the anions, they're negative. And the electronegativity difference between them is approximately 1.7 or higher. And the example I'm going to use here to exhibit this is NaCl, sodium chloride. And so we look at each of these elements. So sodium here has 1 valence electron. It's more likely to lose that electron than to gain more. So when it becomes a cation, it loses that electron, and it has a positive charge. So you erase that, and you put a positive charge. Cl, on the other hand, is the nonmetal. It's an anion. So it starts out with 7 valence electrons here. And so when it becomes an anion, it gains the electron. You could either put it as an X or another dot. And when it gains an electron, it becomes stable. So both of these elements have either a full shell or from the next level or to the next level. So when it gains an electron, it becomes a negative ion. And so this force of attraction here, from positive to negative, opposites attract, which forms the bond between them. Okay? These forces of attraction forms a bond between them. And so you rewrite this for the Lewis dot structures and stuff. Just rewrite it as such. You just bring them closer together. Okay? Now in terms of electronegativity difference, all you're doing is looking up on table S, finding their electronegativities, and subtracting them. It doesn't matter if it's positive or negative, you just look at the number. And they're typically stronger. That means it's a big difference. One takes more control of the electrons than the other. So some of them might be around the 1.7 border, and some of them are higher. Just as long as you're looking between metals and nonmetals. Next one we have is covalent bonding. This is between nonmetals. So you can have multiple nonmetals together, and it's covalent bonds. And they share these electrons. And there are 2 types, polar and nonpolar. Polar is unequal sharing. That means one electron spend more time with one element than the other. And the nonpolar is equal sharing. So it's more like an equal split of the electrons in terms of time spent. So imagine trigger warning. I don't know, it might be a sensitive topic for some, but let's say you have like a pair of divorced parents and you have the kids. So if it's nonpolar, the kids spend equal time between parents. If it's unequal, it's polar, then kids spend more time with one than the other. There we go. Bond polarity here, so determine if it's polar or nonpolar, you have to look at their electronegativity difference. Nonpolars are on the much smaller side, 0 to 0.4, so they're almost equal in that sense. No difference there. Polar, on the other hand, is between 0.4 and 1.7. Exceptions might be those who hover around the 0.4 region, or some of them might be higher than 1.7, but the key thing here is to look at as long as they're nonmetals. So an exception to this would be HF, hydrogen fluoride. That one has a difference of 1.8. So it's still considered a polar covalent bond because you have two nonmetals put together. Hydrogen and fluorine are still two nonmetals together. And the larger the difference, the higher the polarity. So look here, and also the closer it is to 1.7, the more ionic it is. So larger differences lead to higher polarity / more ionic character. Okay? And so here I'm going to draw some examples of some covalent bonds, some covalent compounds here. So here we have got some H2O right here. So H2O has a special shape here, thanks to Vesper. We also got some NH3 here, ammonia. O2 here is two oxygens, double bonded together. And then we got some nitrogen molecules. Nitrogen here has a special triple bond with a single lone pair on each side. So a lot of the ways you could do it is by different methods. There's balance method, Mr. Balance method, where he uses the Lewis electron dot structures, the dots to start forming the structures. And then there's my technique, in which you look at the number of valence electrons, total it up, and then try to distribute it as evenly as possible, trying to achieve all the minimum requirements of octet rule or the 2-electron rule for hydrogen and stuff. And then making sure that everybody's happy here, and making sure you spend all the valence electrons available to you. Okay? And the key thing here is that a bond is shared electrons. It's sharing 2 electrons, whereas a lone pair is unshared 2 electrons as well. So if we look at some of these examples, hydrogen here is bonded to oxygen. So this single bond here is showing 2 electrons. So hydrogen here has access to 2 electrons, it's happy. So is this one, it's happy with 2 electrons. Oxygen here needs 8. So it has 2 electrons access from this bond and another 2 from here, so that's 4. 4 electrons being shared with the hydrogens. Now the other 4 it needs comes from the unshared electrons, the lone pair. So it has 2 here and another 2 here. 2, 4, 6, 8. So oxygen is happy. You could say the same thing about these elements, these compounds as well. So this triple bond here is 6 shared electrons, 2, 4, 6. And then each of these lone pairs comes up with the other 2 needed for each nitrogen. Same thing with oxygen. Double bond is 4 shared electrons, and then these guys need 2 lone pairs each, etc. Now, molecular polarity of a molecule. This is different than bond polarity. So this here, oops, let me use a different color. This here is not equal to bond polarity. So you're not using electronegativity difference here. You're looking at the symmetry of the molecule using the phrase SNAP. So what does this mean? If you break it down, if it's symmetrical in shape, everything folds over neatly, then it's nonpolar. If it's asymmetrical, then it's polar. Okay? So something like this is symmetrical in both ways, but something like this is not symmetrical. It might be symmetrical this way, but it's not symmetrical this way, okay? So pretend you're folding over these dashed lines, folding it in half. That's where you try to see the symmetry there. And so there are different shapes, different shapes of the structures of the molecules lead into the type of shapes, and as a result, different properties as well. So some of the different shapes we learned about was linear. An example of this would be carbon dioxide. Okay. So that's linear, it forms a straight line. Bent is water. That's a classic example you just have to know. There's also pyramidal. I don't know if I spelled that correctly. Oh, it doesn't matter really. So NH3 is an example of that. And then the last one is tetrahedral. Tetra meaning 4. It's a classic example of this. And some of these shapes already come with certain symmetries. Okay? So looking at each of these examples, this is symmetrical. This is not symmetrical. This is also not really symmetrical either, but this is symmetrical. But keep in mind, just because something may be tetrahedral doesn't mean it's always nonpolar or symmetrical. There could be something like this. Here's another example. CH3F, okay? It's not symmetrical, and why? So it might be symmetrical this way, but if you consider it this way, if you fold it over, the H and the F don't overlap. It's different elements, different charge distributions here, okay? So it's not the same. So just because something might have a given shape, the shape doesn't really determine the polarity. It's really the charge distribution and the overall symmetry of it, overlapping elements and such. Next, we have this sort of doozy whopper of an idea called network solids. So they're also covalent compounds, but they cannot exist as singular molecules. So that's supposed to be a S there, singular molecules. What does that mean? Okay, so let's take water as an example, H2O. H2O can exist as a single molecule. That means it exists in nature just like that by itself. However, you're going to have other substances like network solids that cannot exist as a singular molecule, like silicon dioxide, SiO2. Each of these silicon dioxides have to be bonded with others. They cannot exist as a singular molecule, okay, by itself in nature. They're always bonded with others of its kind. The same with carbon. Carbon bonds with another carbon, and they make all these change in special patterns, okay, to form other structures like diamond or graphite. So graphite meaning the pencil lead, and diamonds, of course, your jewelry. And silicon carbide is another example of network solids. So network solids, it differs from other covalent compounds in that they cannot exist as a single unit of a molecule. They have to be bonded together, and that's why they're solids. Now, metallic bonding is a type of bond that exists in metallic substances, and when you have multiple metals mixed together, that's called an alloy. Examples include bronze or brass, or sometimes the coins we have. They're made up of certain percentages of metals in there, not entirely copper and such, or nickel. And so, metals here are strong conductors of electricity, especially in the solid state, because of mobile valence electrons. So imagine you have all these copper atoms here. And so they got their valence electrons floating about here. They're just floating about in their outer shell, you know. And because you have flowing electrons, free mobile electrons floating about and moving, that paves the way for electricity to move and travel. So electricity comes from moving charges. Okay. Another characteristic we have is solubility. So its ability to dissolve and break apart in a solvent, so like water or oil and another liquid substance, okay? So like dissolves like, that's our phrase that we're going to use here. Polar, covalent, and ionic compounds dissolve in polar substances. So polar dissolves polar, ionic can also dissolve in polar substances. For example, water. Water is a polar substance. That's something you definitely need to remember. So polars and ionics can dissolve in water. Nonpolars, on the other hand, only dissolve in nonpolar, so they cannot mix in with water. They can't dissolve in water. But they can dissolve and mix in oil, which is nonpolar. Okay? So here we have this table to summarize the characteristics of compounds. I'm going to fill this in with you guys. So let's start with ionic compounds and melting points. So melting point describes like how high the temperature has to be in order for the substance to melt from solid to liquid. So for ionic substances, this is high. It's pretty low for covalent, but it's also high for network solids and metallic substances. Conductivity, though, sometimes it depends on the different states and phases of matter. Ionic substances cannot conduct electricity as solids, but they can in both the liquid and aqueous states. So that means when you dissolve it in water, then it can be a conductor of electricity. Covalent compounds, on the other hand, are poor. Network solids are also poor, but metallics are strong as solids or liquids even. Okay. Now, can these dissolve in water? That's the question. Ionic, yes. Covalent, polar can. Nonpolar, no. So, but in general, kind of weak. Network solid, no. And metallic, no. And then the last characteristic, hard or soft. Ionic substances are typically hard. They make crystals, crystalline patterns. If you look at it close up, covalent, it's more soft and brittle. Network solids, yes, it's hard. Metallic, yes, it's hard. Oh. Okay. And then lastly, we have intermolecular forces, IMFs for short. Just to summarize that, IMFs. And these are the bonds or forces between molecules. So these are these invisible forces. Well, forces in general are invisible. You can't really tangibly see it or feel it. So the bonds within them are intra. So intra meaning within. The ones between them are inter. So think of the word international, between nations, outside your own country. It's between nations. So the word inter meaning between. So, and we discussed 3 different types in class: hydrogen bonding, van der Waals, and molecule ion attraction. Okay? So just to illustrate the point of inter versus intra, so we have an HCl molecule here. The bond between them is the intra, whereas the dashed line here is the inter. Okay, it's weaker generally, but it exists, and it's a force of attraction. Oh, and one last thing I forgot to mention here. So, stronger forces lead to higher melting points and boiling points, okay? So the stronger the forces, the more energy and heat you need to break them up, so that you need a higher temperature just to dissolve them. So the first type we discuss is hydrogen bonding. Hydrogen likes to have fun. So as long as the molecule includes hydrogen and any of these 3 elements, fluorine, oxygen, and nitrogen, then it has hydrogen bonding. So an example of this would be HF, this one is H2O, and this one is NH3, okay? As long as they have a hydrogen or any of these other three elements. A promiscuous little element. And this is the strongest among intermolecular forces, and it's why water has an unusually high boiling point, okay? And so just to illustrate this with a picture, let's take H2O as an example, all right? Now, because oxygen is more electronegative, think 3.2-ish, and then hydrogen is about 2.2. I could be off by a little bit, but it's around there. So because oxygen is more electronegative, it has more control of the electrons, so it has this partial negative charge. So partial meaning it's not entirely there. So the electrons that go in between both hydrogen and oxygen, they're being shared between them, and so they spend their time not equally though. So they spend more of the time around oxygen than they do around hydrogen. Hence why oxygen has this sort of weak partial negative charge. Then on the other hand, hydrogen here has positive partial charges. It's not definitive like ions, but it's there. And because of this, it kind of creates this sort of weaker force of attraction, hence hydrogen bonding, intermolecular forces. It's not definitive, it's there. So this force of attraction between opposites exists. Okay? And then we have van der Waals. It's a bigger umbrella, and some of you guys from the other classes might have learned the term London dispersion or dipole-dipole. They all fall under this bigger umbrella called van der Waals. And these are just weaker attractions comparatively. And the main idea here is that the forces are stronger when you have bigger size molecules. Okay? So when the size is bigger, the force gets bigger. Okay? So bigger molecules have stronger forces, but it's not that strong comparatively to like hydrogen bonding. Okay? So an example of that is because while hydrogen bonding compounds like H2O, HF, and NH3 might be on the smaller side compared to its other counterparts, because of hydrogen bonding, it has a higher melting and boiling point compared to some of these other bigger sized molecules, okay? And then we have molecule ion attraction. And so this exists when you have an ionic compound dissolved in an aqueous solution. So if you dissolve NaCl in water, it dissolves into the ions and it forms an aqueous solution of the ionic compound, okay? So let's imagine you have this huge block of salt and you put it in water. It's going to cause the ions to break apart, the ionic compound to break apart into its ions, Na plus and Cl minus, and it's going to cause the water molecules around it to orient themselves in a weird way because, again, of opposites attract, opposite charges and partial charges. So Na plus, it's a positive ion. It's going to have the oxygens. Okay, let me draw this differently. It's going to have the oxygens of H2O turn themselves towards it. So these water molecules are just flowing about, but the moment they come in contact with Na plus ion, they're going to position themselves closer to the Na plus ion. And it's because of these partial negative charges. Okay? The same thing happens when you have a Cl minus ion. So all these H's here. They're all going to orient themselves because of these partial positive charges. So that's just the molecule ion attraction. It causes this sort of faint force of attraction because of opposites attracting, and these molecules rearrange and orient themselves into these positions, okay? And that's it.